Chemistry. Why do we need to talk about chemistry if this is a human anatomy and physiology class? Well, chemistry has a lot of things to do with how your body works. So for example, iodine deficiency. Why does that cause a goiter? How does radiation help you diagnose some disorders or help with imaging? Or even, how does all the different components, all the parts and pieces of your body, all the things you eat, end up dealing with how you utilize energy? All those things and more is how chemistry interacts with your body. Because all that food you're eating, well, you need chemistry to make sure you're breaking it down and utilizing those components. So let's start with, what is matter? Matter as in the stuff of the universe, the stuff that's all around us, what we actually are. Matter is going to be anything that takes up mass and takes up space. So we are basically full of matter, in essence. So what are the states of matter? Well, you have solid, liquid, and gas. Now, solid, sure, we're physically solid. At least parts of us are. Solid is going to be something that has a definitive shape and definitive volume. While liquid, which we also are that, think your blood, for example, liquid is going to have a definitive volume, but the shape can change. You're saying, well, shape can change. Well, yeah, if you have a pint of blood, it can take up a bag. It could be in a box. It could be in a cup. The blood can take any shape that's poured into. And then the third phase is gas. Now, gas doesn't have a definitive shape. It can be any shape. Doesn't have a definitive volume. It can be compressed and expanded. Saying, well, what a part of us is gas? Think about inside your lungs. All the air you're breathing, that's gas. When you exhale, you're exhaling the gas partly that you inhaled, but also it's water vapor that you're getting rid of. Carbon dioxide you're getting rid of. So we've got some gas as well inside of our systems that we're breathing in and out and utilizing at that point. Solid, liquid, and gas. 3 states, or the 3 phases of matter. So let's look at the composition. Now, right here we have chemical elements. I'm willing to bet you've heard the term chemical element or chemicals before. But the idea here is, by definition, simplest form of matter to have unique chemical properties. Think periodic table. Carbon, hydrogen, oxygen, nitrogen. You've got helium, you've got argon, you have neon, you have aluminum, you have gold, silver, you have manganese, magnesium. There's so many different elements in that table. Those are the chemical elements. The most basic structures, most basic things that build up to further compounds. Atom. Now the atom is going to be pretty much identical building blocks that can be pieced together. I say pretty much because not everyone's 100% exactly the same. There is a little variation, but we're talking minuscule. So let's look at the atomic symbol. I mentioned already oxygen, carbon, nitrogen, helium, hydrogen, neon, argon. I mean, there's tons of these symbols. They're traditionally 1 or 2 letters that will represent the name of that atomic element. Here you can see carbon, oxygen, hydrogen, and nitrogen. Those are the 4 main elements that make up our bodies. You can see from the bottom here that the actual oxygen is the highest percentage as far as elements go. Then you notice you go up, you have carbon, you have hydrogen, and you have nitrogen. And then in this image, the head shows the others. That's everything else in our body. And there are a lot of other types of elements in our body. So we're looking at these basic building blocks that build pretty much everything that our body's made of. Now, the atomic structure going to have a nucleus, the central core, and then you can have electrons going around it. So the core is made up of neutrons and made up of protons. Now, neutrons are going to be neutral. There's no charge. But the neutrons are each one atomic mass unit, which means each neutron is one AMU, atomic mass unit. The protons do have a positive charge, and each proton you can see here is one AMU also. So for example, if you have one neutron and one proton in the actual core of that element and the nucleus, it'll have two atomic mass units. But then around the outside, we have electrons. Electrons are going to have a negative charge. They don't really have the same weight. As you can see, it says 1/2000th of an AMU, which means you need 2,000 electrons to equal one AMU, so one proton or one neutron. But what we're going to focus on is not necessarily the weight, but the charges. As we move forward in the class, figuring out the charges of these different elements will be beneficial as far as how they combine and how they react in our systems. So neutron, proton, and electron. Neutron, neutral. Proton is positive, electron is negative. When they're depicted, you can kind of see them in one of two ways. Either this one you can see has the planetary model. You have the central nucleus, and then electrons are shown at points around it. Or the lower one, you can see as more of a cloud-based idea, where you can't see any one particular electron. Now that's a little more accurate because the electrons, they're not stationary. The electrons are constantly orbiting and moving around the neutrons and protons, so around the nucleus. So it's more accurate to kind of show a cloud of where they could be at any given moment. But sometimes there's variability, some different takes on each element. These are referred to as isotopes. Now, an isotope is going to be a variation of the same exact element. I'll show you an example in a second. But the neutrons are varying. So you might have one with a set number of neutrons, then one has one more neutron, or two more neutrons, for example. Radioactivity. Radioactivity can go with unstable elements. Sometimes the isotopes are radioactive, which means the isotope with those extra neutrons aren't really stable based for how things are looking here. So here we have an example of hydrogen. The first one, protium, H1, is your standard stable hydrogen. But then you can move on to one that has 2 deuterium and 3 tritium. By having those extra components in the nucleus, they become unstable, which means in the case of tritium, it's radioactive. It's going to try and break down because it's not stable in that configuration. So as we start looking into these, thinking, well, why do we care about radioactive isotopes? Well, the radioactivity and those unstable isotopes that break down, those can help out because when you start looking at imaging, the different radioisotopes can go into your body and then can be tagged to certain structures or certain disorders. Or they can show visualization of the different vessels going through your body, or show the visualization around the different neurons. They can help with identifying and showing us what's inside our body as they give off this radioactivity. Now you're thinking, well, radioactivity, that's bad. It's not great, but small doses aren't going to have a problem. It's if you have constant doses or very large amounts that become detrimental. So chemistry, a bit more to go through yet, but it's helping understand the human body.